Welcome to Physics 100 class. I am Sir Isaac Newton and I will be introducing you to Newtonian mechanics. In case you didn't know, I'm kind of a big deal. I'm going to share a little about myself. I was born the 25th of December, 1642 in England. My father passed away 3 months before my birth. I was raised mostly by my grandmother from the age of 3. My mother wanted to turn me into a farmer, but let's be honest, do I look like the farming type? I excelled in school and later studied at Trinity College and at Cambridge University. My notable fields of study are physics, mathematics, and astronomy. You may be wondering why I am outside with this blustering snow behind me. And even though these penguins are pretty entertaining, that's not why I'm here. I am currently at the site of the Atlantic Ocean where the Titanic hit an iceberg. Now, I know it is a little past my time of living, but here is a video clip from what actually happened to the Titanic back in the year of 1912. For all you romantics out there, this clip isn't all a love story, there is some cold, hard science. While watching this video, look at the physics behind what your eye will see.
Fuck me!
Yes, what do you see?
Icebergs! Right ahead!
Right ahead!
Hard over!
Arms all over, sir!
Thank you, Sir Isaac Newton, for that update. I hope you're staying warm out there. I'm Brock, and I'm going to be explaining Newton's first law of motion. Newton's first law of motion states, a body at rest will remain at rest unless acted upon by an unbalanced force. Also, a body in motion will remain in motion unless acted upon by an unbalanced force. So, motion and rest are interchangeable here, and that is Newton's first law of motion. I am on site here, about to watch a rocket take flight. Let's take a look at this thing. Oh, here it goes. Newton's first law right there. Man, that rocket was fast. Now to explain to you what you just observed and why Newton's first law applies. What you saw was a rocket at rest. It will remain at rest until acted upon by an unbalanced force. So, the thrust was greater than the weight, making the net force positive, causing the rocket to blast off. Whoa! Whoa! Was that magic or was that science? I'm going to go with science because Newton's first law can explain what just took place. The coin stayed at rest on top of the card until acted upon an unbalanced force of me flicking the card out from underneath it, making the coin fall into the jar. Now that's science, not magic. Ooh, he's gonna feel that one in the morning. And I'm sure he's not gonna forget Newton's first law of motion. An important thing to note in example 3 is the man and the sled are not attached. Therefore, as the man and the sled went down the hill, they both experienced motion. But as they got towards the bottom and the sled hit the bump, the sled stopped. Since the man was not attached to the sled, it sent the man farther forward until he laid at rest, causing a crash. Ah! Don't forget now Newton's first law. An object in motion will stay in motion unless acted upon by an unbalanced force. Or an object at rest will remain at rest until acted upon by an unbalanced force. Now on to Al, as he explains Newton's second law of motion.
Hi, I'm Al, and I'm here to tell you a little bit about Newton's second law. Newton's second law states force equals mass times acceleration. How fast an object accelerates depends on the force pushing it. Pushing or pulling an object produces acceleration. An acceleration is a change in the speed of motion. An acceleration can be a slowdown or a speed up. The heavier the object, the more force it takes to make that object speed up or slow down. In this picture, you can see that this young gentleman has a very heavy rock. This gentleman has a much lighter rock. This gentleman right here has to use a much greater amount of force to accelerate this rock across the table, whereas this young man does not have to use as much force. This young lady right here seems to appreciate all this young man's hard work. Another way you can think about Newton's second law is it takes much more of your strength to push a bowling ball with one foot than it does to push a marshmallow with that same foot. So now we're going to get into our first example. For all you Tigers fans out there, how is Justin Verlander able to throw a 100-mile-an-hour fastball? Well, this can be explained by Newton's second law. The object is the baseball. The mass of that baseball is 6 ounces. The force is Justin's arm, and he's able to accelerate the mass of that baseball with such an incredible amount of force. If the mass changed, if say the mass of the baseball was 40 pounds, he would not be able to accelerate the baseball with the same amount of force. And for a little bit extra information, the average high school baseball player can only throw a baseball about 80 miles an hour. So that just tells you the amount of force that Justin's able to create on that ball. So now we have a homemade example of Brock and myself. A little bit about the science behind our little experiment. When I was pulling Brock in the first trial, I did not have to use as much force to be able to accelerate him at an average speed. In the second trial, we added about 40 pounds to the weight that I was pulling, and I had to use a much greater amount of force, and I was not able to accelerate Brock in the chair at the speed that we're able to create before. A real-life application of Newton's second law is, as the price of gas is increasing, people are trading in their trucks because it takes much more force to power their heavier trucks than light cars. The price of gas is astronomical these days, and a little physics can show us that the lightweight car is a better choice. Thanks. It's a little bit about Newton's second law. Now we're going to turn it over to Carrie for Newton's third law.
So I'm going to be talking to you about Newton's third law. Newton's third law talks about action and reaction. So we'll put Newton's third law. So Newton's third law states that to every action there is an equal and opposite reaction. As you just saw in the video clip of Brock and Al, they inflated the balloon and then the balloon was let go. This shows Newton's third law because remember the law states that for every action there is an equal and opposite reaction. So in this example of the balloon was inflated and then let go, so the balloon went the opposite way than the air coming out of the nozzle. So the action in this example was the air coming out of the nozzle, and the reaction, or the opposite reaction, was the balloon going the opposite way than the air coming out of the nozzle. As the video you had just seen, Brock and I tried to throw a trespass to each other, but it didn't work. And instead, the balls collided together, which showed Newton's third law. This shows Newton's third law because remember the law states that for every action, there's an equal and opposite reaction. So the action in this example was that the balls were coming together, and the opposite reaction was the balls bouncing back with force. Gotta get ready to show you Newton's third law. But remember, please don't try this at home. Gotta do a little stretching. Whew. Alright, ready? Here we go. Hey Darcy, do you want to demonstrate Newton's third law with me?
Sure.
Are you sure?
Yeah, why not?
Boom!
Carrie, what was that?
Newton's third law!
Unbelievable.
So, the video you just saw, you noticed that I was pretty mad at my roommate. But remember, not to try it at home. So, you may be asking yourself, how is that example Newton's third law? Well, good question. Let me show you. So to answer your question of how this example shows Newton's third law is this. Force was given from my hand to my roommate's head, which was the action in Newton's third law. And the opposite reaction was my roommate's head putting force onto my hand. So this is how this example demonstrates Newton's third law.
Good job Brock, Al, and Carrie for sharing examples and explaining the basics behind my 3 laws. Now that you have learned about my 3 laws, let's go back to thinking about the video clip from the beginning when I was at the scene of the Titanic. My first law was observed by the ship in motion will stay in motion until acted upon by an iceberg, or an unbalanced force. If the motors were strong enough to reverse the motion of the ship, the Titanic would still be afloat today. For my second law, with knowing how fast the boat was going and knowing how large the mass of the Titanic was, the engine was not able to create enough force to be able to avoid the iceberg fast enough. My third law was shown when the Titanic hit the iceberg. The force of the ship broke the iceberg, which the force was equally as great to break the ship and make it sink. I hope this video helps you become more familiar with my 3 laws. Thanks to Brock, Al, and Carrie, and thank you for watching.